Okay, hello everyone. My name is Karen Yang from National Tsinghua University in Taiwan. And I'd like to first thank the organizers for inviting me to giving me this opportunity to share exciting recent results about the origin of the Fermi and eRosita bubbles, which are one of the most fascinating manifestation of cosmic rays in the Milky Way galaxy. And in the next 25 minutes or so, I would like to share with you our 10-year journey of searching for the origin of these fascinating bubbles. And so this is a work I've done in collaboration with Matej Ruskowski from University of Michigan and Ellen Zweibel from University of Wisconsin in the US. Okay, so this is the gamma ray image of the Fermi bubbles. I believe all of you have seen this picture many times. So the Fermi bubbles are two giant gamma ray bubbles revealed by the Fermi Gamma Ray Space Telescope in 2010. Its height is about 50 degrees in galactic latitude, which corresponds to roughly 10 kiloparsec away from the galactic plane in physical scales. And the gamma ray emission was observed in between 1 to 100 GeV, and the integrated gamma ray luminosity is about 4 times 10 to the 37 ergs per second. And the gamma ray bubble is nearly symmetric about the galactic center, so it strongly suggests that it originates from some energetic outburst from the galactic center, such as a nuclear starburst or AGN activity. And because the Fermi bubbles are so close to us, so we can use them to understand various astrophysical processes like cosmic transport, galactic magnetic field, past galactic center activity, and learn about various processes such as starburst winds or AGN activity. And because it's so close to us, so we have many good spatially resolved multi-wavelength observational data. In addition to the gamma ray map, we also have corresponding X-ray map, microwave haze emission, and also some polarization measurements in the vicinity of the gamma ray bubbles. So we can combine all these kind of observational data to try to constrain the origin of the Fermi bubbles. So here I would like to draw your attention to the X-ray map. So here I'm showing you the X-ray all-sky map taken by the ROSAT mission 20 years ago. And what you're seeing here is the X-ray produced by thermal Brundtland emission by the thermal gas within the Milky Way halo. So as you can see, near the galactic center, actually, the gas distribution within the galactic halo is very, very complex. So if we want to overlay the X-ray emission with the gamma ray emission, that's the gamma ray bubble here, shown in the white contour here, you can see that there seems to be some X-ray emission that's coincident, maybe with the bubble edges. However, in the northern hemisphere, we also notice that there's this very bright arc feature that's called the North Polar Spur. And the North Polar Spur is known to be coincident with the loop one feature in the radial band. And because we know that this loop one feature is related to a local superbubble, so it's intensely debated whether the North Polar Spur is really related to a galactic center event or a more local superbubble event. All right, so from this map, you can see that actually the interpretation of this X-ray map is non-trivial. It's very ambiguous. Okay, so that was the story almost for a long time, okay? Until very recently, so in 2019, eRosita satellite was launched. And although it's currently on hold, unfortunately, but during its active phase of observation, it already revealed very, very striking structures in the Milky Way galaxy. So this is called the eRosita bubbles, which are two gigantic bubbles extending all the way to 80 degrees in galactic latitude, right? So because the eRosita bubble, you can see that it has a southern counterpart. So it's very likely that it's also generated by some energetic event that happened at the galactic center. All right, so this is the outline of my talk today. So first, I would like to tell you about what do we know about the Fermi bubbles observationally? And second, what do we know about the Fermi bubbles theoretically? And third, what does the new eRosita data tell us about the origin of the bubbles? Okay, so first about multi-messenger observational data. Before we try to understand the physical origin of the bubbles, we must understand what the observational constraints are. Okay, so coming back to this gamma ray map, in addition to the symmetry about the galactic center, we also have very good information about its spatial distribution and also spectral distribution. So from the early discovery paper, we already know that actually the gamma ray surface brightness within the gamma ray bubble is nearly flat. So that gives us a very stringent constraint on the 3D distribution of cosmic rays. And across the bubble edges, we also know that the gamma ray intensity has very sharp edges. So that also gives constraints on the cosmic ray diffusion coefficient across the bubble front. And one of the most significant constraints actually comes from the spectra, the gamma ray spectra of the Fermi bubbles. So like what's shown on the bottom left here, the purple line shows the compiled spectrum within the bubbles compared to other diffuse component that's shown in blue color here. So what you can see here is that the Fermi bubble spectrum is very, very hard, much harder than the other diffuse component. And the spectral index is almost very close to -2, indicating that the cosmic rays have not had time to cool yet. So assuming that the Fermi bubble emission is coming from the leptonic model, then actually the cosmic cooling time of high energy electrons will give you very stringent age constraints on the bubble formation time to be within a few million years. All right, so please keep that time scale in mind because that will be very important for our later discussion about different kinds of theoretical models. And later on, in 2014, by accumulating more photons in the Fermi bubble area, basically this work also confirmed previous results. And by getting more photons, we can further divide the gamma ray spectrum into different latitude bands. And basically what is found is that the gamma ray spectrum within the Fermi bubbles is very, very spatially uniform with a spectral index of -2. It's very well fit by a power law. And then there's a high energy cutoff at around 100 GeV, like what's shown here. Okay, so that's the gamma ray spectrum. And in the microwave band, we also observed some haze emission that's called the microwave haze. It was first identified by the WMAP satellite and then later confirmed by the Planck mission. So what was found is that after removing the galactic emission, there's this haze emission that's spatially coincident with the gamma ray bubbles. And the microwave haze also have very hard spectrum. Okay, so it suggests that they share the same origin. And you can also see that instead of the flat intensity distribution of the gamma ray bubble, the microwave haze tend to have decreasing intensity away from the galactic center, which is consistent with the decaying magnetic field strength away from the galactic center. Okay, so let me try to explain this X-ray map again. So this is the ROSAT map again. So from the ROSAT data, we already know that the bubble themselves is underdense because it's not very X-ray bright. It kind of have this Link-Brighton features. So it suggests that the bubbles themselves are underdense. And there's also some arc features like what's shown in the red here, some X feature that's coincident with the bubble edges. So it's suggestive of a shock compressed shell that's pushed outward due to the bubble expansion. Okay, in the TeV gamma ray band, we also have some spatial constraints coming from the Hawk Observatory. So here is the gamma ray spectrum as a function of energy of the photon. And the upper limits represent the upper limits obtained by the Hawk Observatory. So basically what was found is that basically they have no detections above 1 TeV in the vicinity of the Fermi bubbles. And basically, one of their conclusions is that purely hadronic models extending to PeV ranges is disfavored. And by considering multi-messenger observations, we also have some constraints coming from ice cube neutrinos. And so here I'm showing you one example of the plot from Fang et al. 2007, and also consistent with Scherf et al. 2017, which shows that actually the estimated neutrino flux, which is shown in the red bar here, is consistent with the Hawk upper limit. And basically, they've also shown that there's no significant contribution from the Fermi bubbles to the ice cube neutrino flux. And so their conclusion is also that purely hadronic models are disfavored, though hybrid models are still allowed. All right, so let me put all the observational data together into this one schematic view. So here we have the blue showing you the gamma ray bubble, and then we have the less extended microwave haze. And then revealed by the earlier ROSAT mission, we have these X-ray arcs that's embracing the bubbles, although extending to lower galactic latitude. And then with the better data from the eRosita mission, we know that there's this more extended eRosita bubble extending all the way to 80 degrees in galactic latitude. And in TeV gamma rays and neutrinos, so far we have no significant detections from the Fermi bubbles yet. All right, so with this level of details, you can imagine that actually it has been very, very challenging for the theorists to come up with a model that can explain all the observational data. Okay, so let me try to explain what is the origin of the Fermi bubbles from the theoretical point of view. Okay, so from the theoretical perspective, people who come up with models to explain the origin of the bubbles are concerned with mainly the following three questions. The first question is, what are the emission mechanisms? So it can be either leptonic, where the gamma ray is coming from inverse Compton scattering of the interstellar radiation field by the cosmic electrons. And at the same time, these cosmic electrons can then emit microwave haze emission due to synchrotron radiation. And alternatively, the gamma ray can be produced by PP collision, the hadronic process. And due to the pion decay process, we can have secondary electrons and positrons that can then emit in the microwave band. And the second question people are concerned with is what kind of activity at the galactic center triggers the event. So it can be either due to nuclear star formation or AGN activity. And the third question is, where are the cosmic rays produced? So it can be either produced very near the galactic center and then transported outward to large distances, or it can be in situ accelerated by shocks or turbulence near the bubble surface. Know, however, that actually not all these combinations will work, and that's because we have the constraints coming from the hard gamma ray spectrum. So let me give you an example. So for example, say if you want to come up with a model based on nuclear star formation wind, then because winds typically travel at hundreds of kilometers per second, so it will take more than 10 million years to transport these cosmic rays to the bubble surface, and therefore the gamma ray emission has to be hadronic. Otherwise, the cosmic electrons would have cooled. So that is the first type of models called hadronic wind models. And if instead you want to consider a leptonic model, then AGN jets with 10,000 kilometers per second of velocities are required to transport these cosmic ray electrons fast enough to large distances before they cool. So that's the second type of model called leptonic jet model. And if you want to bypass all the age constraints altogether, then you could invoke in situ acceleration models by shocks or turbulence near the bubble surface. And in this kind of models, you don't need to assume any kind of activity near the galactic center as the triggering mechanism. All right, so since the discovery of the Fermi bubbles, many theoretical models have been proposed, and any of those models actually need to fall into one of these three categories of models. Okay, so of course today I don't have much time to go into the details of each type of model, so I will just give you a summary of the current status after people's various works. Okay, so first of all, what previous studies have found is that actually the hadronic models have been disfavored. So, like I said, the hadronic model is basically inconsistent with the Hawk upper limit and also the ice cube estimated ice cube limits. And also, it was shown by previous work that the hadronic model cannot actually fit the microwave haze spectrum, and that's because if they calculate the emission produced by secondary electrons and positrons, then the predicted amount of emission falls short compared to the observed haze spectrum, and also the slope is too soft compared to the observed hard spectrum. Okay, so basically, people have found that the hadronic model has been disfavored. So now we're left with the leptonic jet model or the in situ acceleration model. Okay, so let me try to explain the status of the leptonic jet model first. So in terms of this model, various studies, including earlier 2D hydrodynamic simulations and my own 3D MHD simulations have found that the leptonic jet model have been quite successful. So we assume that the initial jet speed is on the order of thousands to 10,000 kilometers per second. And indeed, we showed that the bubbles can form within a few million years. So that satisfied the age constraints that we discussed earlier. And in particular, we showed that with this leptonic jet model, the gamma ray bubble, and the microwave haze spectrum can be simultaneously reproduced by the same population of cosmic ray electrons. Okay, so basically we've shown that, okay, the leptonic jet model worked quite well. And how about the third type of model, the in situ acceleration model? So it was shown by this work, Mertz et al. 2018, that actually it's also quite successful. Okay, so in this work, they've assumed that the cosmic rays are injected at the shock and accelerated by turbulence in the shock downstream. And by assuming certain geometry for the magnetic field and also some combination of cosmic diffusion coefficient, they've shown that actually their model can also reproduce the spatially uniform gamma ray spectrum and the microwave haze spectrum. All right, so basically we found that, okay, both the leptonic jet model and the in situ acceleration models can work. So now the important question is which model is correct, right? Okay, so let me come back to this cartoon again. So in terms of predicting the non-thermal emission in gamma ray band and microwave band, actually these two models are both very successful. But if you think about it, then there's a very key difference between these two models, which is the location of the shocks. So for the in situ acceleration models, because it's assumed that the cosmic rays are accelerated by shocks or turbulence in the shock downstream. So in this model, the shock front should be coincident with the bubble surface by construction. Okay. However, on the other hand, for the leptonic jet models, in typical scenarios, the forward shock can be more extended than the surface of the Fermi bubbles, which represents a contact discontinuity between the jet material and the shocked ISM. Okay, so the location of the shock is one key ingredient if we want to distinguish the leptonic jet model with the in situ acceleration models. Okay, so the key question is where is the shock? Okay, so where can we find it? We can again go to the X-ray band, right? Okay, so let me come back to this Rosette X-ray map. So with the Rosette data, it's not so clear whether this arc feature is coincident with the bubble surface or more extended because of the limited sensitivity. However, with the new eRosita bubble, we can clearly see that its surface is more extended than the gamma ray bubble itself. Okay, so if we overlay these two maps together, The red color shows the gamma ray emission, and the cyan shows the eRosita bubble. Then we can clearly see that these two surfaces are not the same. Okay, so the most likely scenario to explain both the X-ray emission and the gamma ray emission is that the eRosita bubble represent the forward shock driven by the bubble expansion, and the Fermi bubble correspond to the contact discontinuity between the jet material and the shocked ISM. Okay, so when I saw this picture in 2020, I was very excited because this alone suggests that the leptonic jet model could work. Okay, could be very successful. So I went back to my previous simulations again and tried to find what kind of jet parameters can actually reproduce both the location of the Fermi bubbles and the morphology of the shock front. Okay, so indeed, I found one parameter set that can fit the morphology for both bubbles. Okay, so here I'm going to show you a short animation made from my revised simulation of the Fermi bubbles. Okay, so let me play this animation. Okay, so what you can see here in the color on the outskirts is the shock front that's propagating outward, expanding into the galactic halo, driven by the central AGN outburst. And the red color here shows you the customary distribution at the end of the simulations. And in this kind of simulations, we assume that the customaries are injected at the galactic center via AGN jets. And then in this kind of modeling, we actually keep track of the customary energy evolution, the spectral evolution of cosmic rays via multi-fluid approach. So in our simulation, because we can simultaneously model the cosmic spectrum and also the thermal gas distribution, so we can compute the non-thermal emission from the cosmic rays and the thermal emission from the thermal gas simultaneously and self-consistently. All right, so what is the result? So let me show you, show that summarized in one slide. So basically what we found is that all the X-ray, gamma ray, and microwave data are very well matched by the leptonic jet model. Okay, so like what's shown here is the simulated X-ray map that's shown in the yellow and blue color here, overlaid with the predicted gamma ray emission shown in red here. So you can see that the morphology of the bubbles are well reproduced. And bottom left here is the broadband spectrum from our simulation. And you can also see that they match with the spatial data quite well. And on the bottom right here, I'm showing you the profile of the microwave haze emission and also the profile of the gamma ray emission. And they also give very good fit. So overall, we find very good agreement between the leptonic jet model and the multi-wavelengths of spatial data. All right, so this result is recently published in Nature Astronomy and also featured in many scientific media. So if you're interested, please feel free to check it out. So from our simulation, we can get a few very important constraints about the jet activity that's generating the Fermi bubbles and eRosita bubbles. So what we've learned from our simulations include that the jet occurred roughly 2.6 million years ago, and the jets were active for a short period of time of roughly 0.1 million years. And the inferred Eddington ratio of black hole accretion is roughly 1 to 10% of the Eddington rate. And interestingly, actually the timescale and the inferred level of activity is very consistent with another independent constraint coming from the ionization signatures in the Magellanic Stream. So Bland Hawthorne et al. 2013 and 19, they've discovered that actually there's enhanced H alpha carbon and silicon ionization lines, suggesting that the galactic center might have gone through a past Seyfert flare activity. Okay, so they use this kind of highly ionized signatures to quantify the activity level of the central black hole and the constraint Eddington ratio and also the age of the event is also very in good agreement with independent constraints coming from our modeling of the Fermi bubbles. Okay, so combining all these hints together, it seems to suggest that our central supermassive black hole really had a Seyfert flare-like activity a few million years ago. Okay, in summary, I've shown you that the multi-wavelength observation of the Fermi and eRosita bubbles are likely caused by a single outburst of jet activity of Sagittarius A star, and the inferred age of 2.6 million years and antigen ratio about 1 to 10% are consistent with enhanced ionization in Magellanic Stream, pointing to a safer flare activity of Sagittarius A star. All right, so now I've shown that it's very likely that the Fermi bubbles are generated by AGN activity in the past. So we can start to ask a few interesting questions, such as whether these kind of bubbles can be seen in nearby galaxies. So recently, we've conducted another study led by Alice Owen, who is a SICA fellow at NTHU, and so he ran our same simulations in the Galatis Fermi bubble condition and evolve it for longer and then predict the multi-wavelengths of observational signatures on longer timescales. All right, so we want to see whether this kind of bubbles, similar to the Fermi bubbles, can be actually observed in other galaxies as well. Okay, so basically what I'm showing here is the predicted broadband spectrum coming from this kind of leptonic galaxy bubbles, similar to the Fermi bubbles. And what we found is that, unfortunately, in the GeV and TeV bands, leptonic bubbles really decays very, very quickly due to synchrotron and inverse Compton cooling. So even given the sensitivity of CTA, only a few will be observable. However, in the radio bands, the detection prospect is much greater because the radio emission drops relatively slowly. And given the sensitivity of SKA, for example, a few dozens would be observable. And finally, let me give you a little advertisement here. So the MHD plus customary spectral evolution code can not only be applied for modeling things like the Fermi bubbles, but it can also be a very powerful tool for modeling the non-thermal and thermal emissions simultaneously for a variety of astrophysical systems, including galactic winds, cluster radial bubbles, supernova remnants, and active galactic nuclei. Okay, so if you are interested in applying this kind of simulation code to your favorite systems, I'll be very, very happy to discuss with you. Okay, I'll end my talk here. Thank you very much.